Hello and welcome. In this video, we're going to cover Module 7 or Chapter 7, Ethernet Switching. So in this module, it's the part of the CCNA Introduction to Networks. So Chapter 7 in CCNA Introduction to Networks. So in this module, you'll learn a couple of things. So we're going to learn the Ethernet frame. So there are a couple of fields in the Ethernet frame that we're going to mention. Going to learn also Ethernet MAC addresses. So as we mentioned in the explanation of the OSI and TCP/IP, at the frame, basically the source and the destination MAC are added. And then the MAC address table, how switches actually learn the MAC addresses and build MAC address tables, and the forwarding, the switch speeds and forwarding method. So let's get started. The Ethernet frame, as you can see, the switches, they operate at the data link layer, or I should say the layer 2 switches, they operate at the data link layer. So the data link layer is subdivided into two layers. As you can see, the logic link, which provide the logical link to the upper layer network layer, and then the MAC addresses, okay, source and the destination right here. So yeah, let's go to the next slide. So as you can see here, we have the logical link sublayer and we have MAC sublayer, and that's the data link, the layer 2 of the OSI model. So as you can see here, this is the Ethernet frame field. You need to remember the Ethernet frame fields. So as you can see here, we have the preamble and the SPD, as you can see. Then we have the destination MAC address added to the PDU and source MAC address, the type and lint. So the type and the lint, and then the data, and then frame check sequence is added at the data link layer. Frame check sequence, basically, it's a trailer added to detect if there are errors, okay, caused by collision or caused by bad cabling, and so on. Ethernet MAC addresses. So MAC addresses are basically a 48 binary bits, and they are written in hexadecimal. So let me talk a little bit about MAC addresses. So MAC addresses, as I mentioned, are written in hex, and they are 48 bits. For example, let's say this could be a MAC address 0001111.2222. That could be a MAC address. They are written in hexadecimal. So as we mentioned before in the previous videos, each hex digit represents 4 binary bits. Okay, so 4 multiplied by 12, the total of 48 binary bits. So binary bits. That's the MAC addresses. There are two notations I should mention. So we have the Cisco notation. So Cisco writes the 4 digits, 4 hex digits, and then the dot, okay, and then separated by 4 digits, and then another dot. The MAC addresses also, they have two portions. One portion is called organizational unique identifier to identify the organization, and then the vendor assigned. So the vendor of the MAC address, vendor assigned, is also assigned by an organization as well. So the first 24 is organizational unique, and the second 24 bits are the vendor assigned. So I should talk about the notation. So Cisco notation writes the 4 digits and the dot, as you can see, 4 digits and another dot, and 4 digits and another dot. Microsoft notation, 2 digits and then the dash right here. Okay, so after each 2 digits there is a dash. For example, let me bring my CMD in here. So let me show you how the Microsoft notation looks like. regarding the MAC addresses. So yeah, so I should actually use the ipconfig/all. So ipconfig/all, and notice that I'm using, let me get my Ethernet adapter here. So this is the adapter that I'm using. As you can see, Ethernet adapter, and you see here physical address. So that's the physical address, and that's the Microsoft notation. So after each 2 hex digits, there is a dash between them. And to know the MAC address, for example, you could actually copy this one and go open a web browser if you want to check what manufacturer of your MAC address adapter. So we check the MAC address lookup. Let's use MAC address, okay, lookup website, and then we could check our manufacturer of the MAC address. So based on the organization you need unique identifier and the vendor assigned, as you can see, it says Dell EMC. So this MAC or this network card, and using the MAC address is actually manufactured by Dell INC, as you can see. Okay, so yeah, that's the physical address, and that's the Microsoft notation of MAC addresses. So so as you can see here, so each hex digit represents 4 binary bits. And then let me actually go and explain how the switches. As you can see, this is a PDU. This is a PDU. We have the data itself coming from the application layer. And then at the transport layer adds TCP or UDP plus the port number. And then we have the network layer or internet layer of the TCP IP. So, and then at the MAC or at the data link layer, the MAC address, the source and destination MAC are added into the Ethernet frame. Okay, so yeah. So the MAC address table. So I'm going to explain here. I'm going to actually get my black screen, and then let me show you a couple of things which are important in this chapter. So let's say we have a PC in here, okay, connected to a switch, and then let's say this is PC1, okay, and then we have a switch in here, and then let's say we have PC2, okay, connected to PC2, connected to the same switch, and then PC3, for example, right here, and then this is PC3. PC1 is connecting to the switch via FA0/1, fast Ethernet 0/1, PC2 fast Ethernet 0/2, and then PC3 is connected to the switch via fast Ethernet 0/3. And then let's say we have a router right here, okay, the default gateway. So what happened when PC1, let's say PC1 with a MAC address that starts with 111 and 1, for simplicity, I'm going to write the entire MAC. PC2 MAC address starts with 222 dot, and I don't care about the rest. And then PC3 the MAC address starts with 333, and then we don't care about the rest. So what the switch will do, as you plug the PC into the switch immediately learn the source MAC address. So let me change my color here. Okay, so as the PC1 send a frame, okay, to the switch will get the MAC address of PC2 and actually put it in MAC address table. So it will say 1111, okay, and then the rest is connected to me via fast Ethernet 0/1. And then the PC2, when it's actually when you plug PC2 into the switch, then it will get the MAC address. Switch will get the MAC address, and then associated with the port number fast Ethernet 02. And then the MAC address of PC3 will be associated with fast Ethernet 0/3. 3. This way, when the switch gets, let's say, frame destined for PC2 from PC1, so this is the source. Let's say this is the source and this is the destination, then the switch will actually open the MAC address table and sees that PC3 is connected via fast Ethernet 0/3. Then the switch will immediately forward the frame, okay, on port fast Ethernet 0/3 exactly and only to PC3. So that's actually how the switches, they build MAC address, how they learn MAC address table. So they learn MAC addresses based on a source, and they forward frames based on the destination MAC address, and they build what is called MAC address table, and this is the MAC address, okay, table. Yeah. So what's happened if we're talking about unicast? So PC1 with PC3, so that's unicast communication, one-to-one communication. What if PC1 want to send a broadcast? Okay, the broadcast, for example, the R protocol. So the R protocol is sent as a broadcast. The broadcast will be sent from PC1 to all devices on the network. Also, the router will get the broadcast. So the switch, how actually will treat the broadcast? So when the switch receives the broadcast on fast Ethernet 0/1 port, the switch will forward the broadcast all ports except the port that the broadcast was received on, except this port right here. Okay, this is exactly the case if so we talked about unicast. So unicast is actually one-to-one, okay, one-to-one communication. Broadcast, so broadcast is the broadcast, okay, is one-to-all, and then we have the multicast is one-to-many. My point that I want to make right now is actually the switches, they treat the broadcast and the unknown, okay, unicast frames the same. So what about if the switch, for example, receive a frame, I don't know, it receives a frame with unknown destination MAC address. In this case, the switch will forward the frame all ports to make sure everybody will get the frame except, okay, the port that was receiving the broadcast, the unknown source MAC address on. Okay, so we have three scenarios: one-to-one communication, unicast. Okay, known unicast frames are sent exactly to the destination based on the MAC address table. Unknown unicast frames are treated exactly like a broadcast, and the broadcast, of course, the switch will broadcast it to all ports except the port that was receiving the broadcast on. Okay, so let's actually move to the slide. I hope this actually makes sense to you. So that's how the switches operate. So let me go to next slide. So switch learning and forwarding. So we talked about that, we explained it. So let's move forward. For example, here in this diagram, as you can see, so we have the PC sending a frame on port 1. So when the switch will get the frame, will actually let's say the source is this one and the destination MAC is 00D. So in this case, it will actually look at the MAC address table and see that 00D is associated with port number 4. Then the switch will forward the frame, okay, on the exit port, okay, 4 at this point. For example, let's say the source MAC is this MAC address right here, okay, and the destination MAC will be 000B. In this case, the switch will forward the frame all ports, okay, to all ports, because it's unknown MAC address, unknown unicast MAC address. So let's move forward. So switching speeds and forwarding methods. So there are two forwarding methods. There are actually the store and forward, as you can see, as the name implies. So it's self-explanatory. Store and forward. So store the entire frame in the switch and then start forwarding before. Okay, yeah. So it needs to store the entire frame. You need to receive the entire frame and then start forwarding the frame to the destination. And then cut through, basically switching is a process of start actually sending before it receives the entire frame. That's the two concepts, and you need to know that for the exam. So you need to distinguish between cut through switching and store and forward switching. Memory buffering on a switch. So we have two types of memory buffers. We have port-based memory buffer. So this means that each port on a switch have a buffer or a queue. Okay, so for example, if the switch is connecting to a voice over IP phone, and as you may know, voice over IP phones, they have a port where you connect a PC on to that port, okay, and then you connect the voice over IP to the switch itself, okay. So you have two devices. So one communicates on a native VLAN, which is the PC in this case, communicates on native VLAN, but the voice over IP communicates on the voice VLAN. So we have voice VLAN and we have native VLAN right here. So in this case, the voice traffic received by the port will be sent as fast as possible, but the traffic coming from the PC will wait in the queue, and this is using port-based memory, okay? And then we have shared memory. Shared memory is basically a queue for the entire switch, and I mean for the entire switch ports, okay? So it's built-in queue, and if it receives traffic destined for voice or video, then it will send it as fast as possible. Or if it receives like FTP, HTTP, email traffic, and so on and so forth, it's not going to forward it. It's going to wait in the queue, okay, and prioritize the voice traffic. So the speed and duplex. So the duplex, actually, there are two speeds. So we have the duplex, two types of duplex. So let's say we have a switch SW1, and this SW1 is connected to SW2, for example. So the duplex, basically, in case of gigabit Ethernet, so these switches are actually capable of forwarding with 1 gig per second speed. They have 1 gig per second speed ports. Then you could configure the duplex as full duplex. So full, and don't allow them to negotiate. You could actually, if you have a switch that can operate at full duplex on one side, and you connect an old PC or old device that actually can only operate at half duplex, then you need to configure half duplex right here. So half duplex here and half duplex on this side to don't cause any collision. The full duplex, basically, the port can send and receive at the same time, while the half duplex can only send or receive at a time, or receive. So it cannot send and receive simultaneously. It needs, if it's sending, then it cannot receive. If it's receiving, it cannot send. So what happens if you have, for example, switches connected like this? So let's say this is a switch, gigabit Ethernet, this side is full and this side is half, then this side will be overwhelmed. So this one can send and receive, but this one can only receive at a time or send at a time. Then this actually cause collision on the other side. That's why you need to hard code the speed. The speed could be 1000 meg per second speed, which is 1 gig. Could be 100 fast Ethernet, is gigabit Ethernet, fast Ethernet, or 10 meg per second, which is Ethernet. So gigabit ports, they operate at full duplex by default. The Ethernet, they operate at half duplex by default, so you need to hard code the speed and duplex. So I hope this had been informative for you, and I would like to thank you for viewing.